Welcome to constant coefficient homogeneous ODEs and the characteristic equation. So recall for second order, if we had AY double prime plus BY prime plus CY equal to 0. What we did was we assumed that Y was equal to e to the Rx. And then we got the characteristic equation. AR squared plus BR plus C equals 0, which could be used to find such solutions. We can absolutely generalize this to constant coefficient equations of any order. So instead of A, B, C, we're now going to just use, say, A sub 0. So let's say, so if we have an nth order linear constant coefficient, homogeneous, ODE, then what we're looking at is we have, it takes the form A naught times the nth derivative of y plus A sub 1 times the n minus first derivative of y plus all the way down to A sub n times y equals 0. Again, because we're doing nth order, we can't do ABC since that's specific to how many terms we have. Right? So if we then assume that y is equal to e to the Rx, right, then what we get is that the kth derivative of y is just r to the k times e to the Rx. And so we are looking at A naught times r to the nth times e to the Rx plus A1 times r to the n minus 1 times e to the Rx plus all the way down to A sub n e to the Rx equals 0. And this means that A naught r to the n plus A1 r to the n minus 1 plus all the way down to plus A sub n must equal 0. And so again, we have our characteristic equation. So we once again call this the characteristic equation. And we get a fact if the characteristic equation has n distinct real roots. So if the characteristic equation has n distinct real roots, R1 through Rn, then y1 equaling e to the r1x through yn equaling e to the rnx form a fundamental set of solutions. So for example, let's go ahead and find the general solution of the third derivative of y minus 2 times the second derivative of y minus y prime plus 2y equals 0. So we have characteristic equation. R cubed minus 2r squared minus r plus 2 equals 0. This can be factored using what is called a factor by grouping. So r squared minus 2r squared, we're going to lump together, and negative r plus 2 we are going to lump together. We have r squared times r minus 2, and then minus 1 times r minus 2 is equal to 0. If r minus 2 and r minus 2 match, we can go ahead and factor them out. And we have r minus 2 times r squared minus 1 is equal to 0. Or r minus 2 times r minus 1 times r plus 1 is equal to 0. Thus we get r is either 2, 1, or negative 1, and we have 3 distinct real roots. Using that, we get our fundamental set of solutions. Y1 is e to the 2x. Y2 is e to the x. And Y3 is e to the negative x. And so we wind up getting there for our general solution. Y is equal to C1 e to the 2x plus C2 e to the x plus C3 e to the negative x. As you can see, we will be having to do factoring of third and fourth degree polynomials, which is not always the easiest thing to do. In the next video, I will do a little review of factoring techniques that we can use for those higher degree polynomials. Once we have our characteristic equation factored, then at least in the case where we have distinct real roots, we now know how to find the solution to that homogeneous constant coefficient linear DiffODE.